All right. So let's go ahead and get started. I think that what I'll do is I will emphasize the two orange workflows that I put together. And maybe not, since I sent you the chapter, you've got that if you want it anyway. So why don't we start with class imbalance? The best demonstration for this is an actual data set. You all have heard of the Framingham Heart Study. It started back, I believe, in the 1940s. So here it is. It's available in Kaggle. So that's where I got it. Kaggle, if you don't know, is this gigantic data competition website. I mean, it is really something else. And they have several thousand data sets, and you can compete. In fact, we figured out a way to have Orange compete in it, even though most people would submit programming. But anyway, so this came from Kaggle, and basically it's 4,200 patients followed for 10 years. The outcome or target is they develop heart disease, yes or no. Okay. And some of the parameters are fairly standard, if you will. And so, but let's look, when I say class imbalance, I think the quickest way is actually a box plot where you select 10-year heart disease. You're looking at the target and you go, you're interested in the people that develop heart disease, that's red, 644, but the people that didn't have heart disease is 6 times that. Okay, so that's class imbalance. Then you say, well, how do you define class imbalance? There is no perfect definition. Is it greater than 3 to 1? You really can't say. So, in a way, one of the ways that I would say, and particularly if you're looking at a published study, is go to the actual results and what you're going to see. And let's take either what I have done here is logistic regression. I've clicked the button that says balance class distribution, and for random forest, I clicked that button. So we'll compare them, but the point is, let's just look at the one where I have not clicked that button. So the AUC and classification accuracy is not too shabby, but look at the F1 score. It ought to be 0.8, something like that. Precision is good, but recall is abysmal. What does that mean? It means it picked up a few positives, and those positives are truly true positives, not false positives. But look at the sensitivity or recall. It's horrendous. We're going to talk about clicking the button here in a second, but notice the difference. It really did make a gigantic difference. We're also going to test on the test data rather than the training data. But let's go back to start over again. So we've got class imbalance. 6 times more people without heart disease than with heart disease. There are some missing data points, so we're going to impute those, so that's not an issue. We're going to split it into 70%, it doesn't make a lot of difference. 70% training, 30% test. But what we're going to do is use two kinds of logistic regression. One is the regular, but in this one, we're going to click balance class distribution. It gives more weight to the minority class, which is those people with heart disease. In random forest, same thing. I've clicked that same button, okay? So again, here's the reminder. Class imbalance causes a falsely high AUC accuracy and specificity and falsely low recall and precision. And also you might say, well, how did I write that? Just remember, you can rename it. So it could be whatever you want. Likewise, remember duplicate so you don't have to go find another logistic regression. You just duplicate it and rename it. So that's how we got there. So let's look at test and score again. And a point that I'm going to make is when you have this scenario, you need to look at different things. One of them that's practical is the F1 score. Why? Because it focuses on the positive class of precision and recall. It's kind of, they call it the harmonic mean. I'd call it's a compromise between precision and recall. So you want a high F1. It's that simple. Now, the Matthews correlation coefficient is interesting because it looks at the majority and the minority. So you would like that always as high as you can get it. So when you look at with and without the clicking the button, you want to look at the highest F1 score. Well, clearly it's logistic regression with the balanced class distribution option. But notice, so the recall is the highest and the MCC is the highest. But I will draw your attention to the fact that precision's not the highest because you've probably pulled in some more false positives, unfortunately. And you might say, well, how can you get a visualization? Simple. Our buddy, the confusion matrix. So let's look at, for instance, logistic regression here, plain old regression. Notice it's only 13 true positives, not many false positives, but a ton of false negatives, right? Look at balanced class distribution. Did much better. You sucked in way more true positives, but more false positives. So, but I wanted to again get you to understand. I know the confusion matrix is confusing, but once you've done it, it's not. It predicted one, but it was zero. So that's a false positive. It predicted zero, but it was one. It's a false negative. So it's really not that complicated. So we'll go over a couple of other important points. So we say, okay, let's not dwell on AUC and accuracy. What else should we dwell on? I've mentioned F1 score. I've mentioned Matthew's correlation coefficient. Here's another one. Rather than dwelling on the rock curve and area under the curve, guess what? There's a precision recall curve. This is what you should be looking at. And this is more or less the mirror image of a receiver operator curve, right? And here gives you the area under it. Now, the only reason you look at that is these numbers don't mean a heck of a lot to you, okay? But basically, you want the highest area under the curve, and it looks like for this, logistic regression and logistic regression with class distribution are about the same. And let's compare that. Now, this, by the way, this hash line down here indicates the area where it no longer has meaning. If your curve is down here, then it's just a guess in terms of trying to separate the classes and whatnot. The same would be true of the receiver operator curve. So this is mediocre. It's not great. It ought to be up here where the true positives are high and the false positives are low. This is a curve of meaninglessness. So if you have a curve that's down here close to this, your model is not performing. It can't separate those with heart disease and those without. That's what that means, basically. All right, so precision recall curve is what should be reported in an article like that. Now, there's another interesting thing here. When you go to the calibration plot, you can select other things. For instance, notice this drop down. We're not going to talk about calibration curve, but notice this other stuff. I mentioned F1 is not a bad measure. So let's say you take the highest performing model, which seemed like overall was logistic regression, and then you can change the threshold. Again, I have no clue how you do that in Python. I'm sure you could tell AI to do it, but the point is, I'm sure it's labor intensive, but watch, you just shift it. You shift it and look to the left. Notice logistic regression, I think was started at 392, and you go right and left, and there it is at 401. So the answer, and that's not a huge big deal, but the point is, so the threshold moved a little bit to the right, gave you a higher F1 score of 0.401. In some instances, it's going to be different than that. Also, getting back to what I said many sessions ago, don't have any strong preconceived ideas that a certain combination is always going to do best. In data science, you're going to be wrong a lot, meaning you don't know that logistic regression with this clicked is best. I think when we look at random forest here with that button clicked, it didn't do much. Look what it did. Actually, recall got lower. So the point here is there's a tremendous amount of trial and error in data science with which algorithm you select, how you adjust that algorithm, and what performance measures you select, like precision recall. That makes this somewhat frustrating. And again, AI will probably make that easier for you when it says, I'll look at 6 parameters, I'll select the best, and I'll tell you what's the best. Otherwise it's time consuming, tremendously time consuming in programming. So again, then you might say, well, okay, but we've now said that we've shifted the threshold. How do we keep that and use it on the next model? The answer is you just save the model. That's what this is for. And then you can load the model as another widget, okay? And I showed you that 2 sessions ago, I think. All right, so now to even add more confusion, we've said that the F1 score is probably the best. Orange doesn't have F.5 and it doesn't have F2, but it does exist. You should know that. I'm sure Python has it. Some of the more expensive, elaborate programs have it. I'm just educating you that, for instance, if you want more weight to precision, 0.5, more weight to recall, F2. Just be aware of that. Also, this is not in the book, but it's pretty simple-minded. As you compromise, uh, well, it is a compromise. As you do things to this data set, you might see, for instance, notice the recall got much better with balancing class distribution, but look what happened to specificity. Took a nosedive. And that frequently happens. It's a compromise. You can't have your cake and eat it. That's why they came up with this no free lunch theorem. So when you do balanced accuracy, it's sensitivity plus specificity divided by 2. So that all this would do is say, overall, what's the best compromise? That's all this does. So if you had 6 models and you wanted to compare 6, you might look at balance accuracy to see which is the highest. Just gives you one more measure. And then you might say, well, can you calculate the best threshold? Yeah, you can. Here are 2. We won't calculate these. It's in the book. There's a geometric means, which is just the square root of sensitivity times specificity. And there's the Uden J index. Just be aware that that exists. Make no effort to memorize it. All right, then we're going to shift gears. So we talked about balancing, which is, by the way, probably the no-brainer approach, the simplest. Nobody can argue with that, by the way. We talked about threshold. That's not unreasonable as another way to make this better. Now we'll talk about SMOTE. SMOTE stands for synthetic minority oversampling technique. Oversampling means you take this minority. What if we could increase this? We could study its buddies, and that's what we did. We used K nearest neighbor. We measured distances. We found some cousins. Okay, now look. All right, now we got exactly the same number of people that developed heart disease that didn't, because we created some synthetic data points that look an awful lot like the original, okay? Now, the criticism of SMOTE, I mean, it's perfectly reasonable. In fact, let's look at the results, at the test data once again. So let's look at, so recall seems to be much better, but what about the F1 score? I don't think so. Now, random forest for the F1 score is good, but here it's almost too good to be true in the sense that your A1C, or excuse me, AUC is high, specificity is high. So I would have to look at this in detail, by the way. This is so good. I'm really kind of almost don't believe it because, and also not only that, I mentioned it can cause overfitting. Well, how you normally check on that is you look at training. Let's look at the F1 on training and see if it got worse with testing. So 891, I think it went up. Yeah, so my point here is it does look like smoke is the best of all. Okay. However, when I see a result that good, I have to question it. I'd have to test it in some other way. For instance, I'd have to go back to the data set, which I've not done, and look for duplicates. For instance, maybe it's simply copied. And instead of finding cousins, it just simply copied existing. I would worry about that, to be honest. So again, and by the way, I have a smoke widget that we created. I did not, for time's sake, I did this a while back with AI. So I probably will now, not tonight, I'll use the smoke widget and see if I get a similar result. Uh, and anybody's welcome to it. I'll be happy to send it to you. Uh, what we did is we took the Python widget that exists and we had a programmer create the smoke widget. So anyway, let me just say that smoke is an option, but always question the result of everything you do and double check it if need be. All right, lastly, so smoke basically took the minority class and magnified it by picking similar data points, right? What happens if you do the opposite? You decrease the majority. So what does that look like? I've decreased from 3,500, these people without heart disease, to 728. I've kept the minority of people with heart disease the same. Now, what's the risk of that? Everybody would tell you, well, you've now decreased the number of people that could decrease the power of your prediction. So let's just see what we have. It's the same setup, logistic regression, random forest. Let's look at test data. This is test data. So what do we have here? Let me blow that up. So the MCC is not very high. The recall for logistic regression is pretty good. Precision is pretty good. F1 is 628 is not too bad. AUC is not too bad. Specificity took a bit of a nosedive. But let's just, one thing I didn't do for the fun of it. So let's see, wait a minute. That random? What was the best F1? Okay, logistic regression. Let's go ahead and click. That was 628, I believe. Oh, no wonder. I'm sorry. Class distribution is still clicked. Let's unclick it because I made, wait a minute. So it was unclicked for random forest. So let's look at it again. So you can do it with or without. So it looks like, I think we were 628. So again, it did much better. So you can do combinations, but in general, people do not like to do this. This is not recommended, but it is an approach. I mean, for instance, what if you had, instead of this, uh, that's not what I want to show. What if the scenario was that you had 50,000 people without heart disease and 10,000 with heart disease? It'd probably be legitimate to do this. You know, you'd have enough people with heart disease that you wouldn't worry about it. But, you know, always remember when you do the test data, remember the test data is only 25% of the total, right? So you start decreasing the numbers. And let's look at that in the confusion matrix. So here, it's not too bad. So for logistic regression, the true positives is 97, not terrible. And, again, false positives 60, false negatives 64. Notice the true negatives only 122. So again, and you can mix and match, meaning you could use SMOTE with or without clicking class distribution or balanced class distribution or whatnot. But I just want to emphasize, number one, that experimentation in data science is really important. Rather than saying, oh, I always use logistic regression and I always set it on lasso, forget that. You have to try a bunch of different algorithms. You have to adjust, but many of them use as many options as possible before you decide you really have hit, a home run. So I think that's a logical stopping point about class imbalance. Any questions about that?
Dr. Hoyt,
And
I
yes.
have a question. So, can you do like SMOT and undersampling in orange? Both?
Uh, can you do smote with what?
SMOT and undersampling in the orange
Well,
software?
no, but I'm
Okay.
glad you mentioned it though, because in the book I mentioned the fact, understand that some people will do undersampling and oversampling simultaneously. There are
Okay.
packages out there, and I mention it in the book. So in Python, you could try one of the packages that does both. Now, what
Okay.
I had to do for the undersampling, and I should have mentioned it, is I literally today went into the original data set. I sorted it 0 and 1, and I took out like 2,500
Oh,
2,500 zeros.
okay.
Uh,
Okay.
that's how I came up with this data set that I showed you. I manually
Written
did
that.
that. And again, you don't know. I called that random. It might not have been random for all I know. So
Mhm.
that's one of the hazards of doing what I just did.
Okay.
But that's how I came up with it. But no, Orange does, and Orange does not have smoke. We created it, just so
Okay.
you know. We wanted it. And so we figured out how to create our own smoke widget.
Okay.
This smoke is basically I had Visly create it. It said it uses smoke and
Oh, okay.
exported it. It
Okay.
really was pretty seamless. But again, I think the results are so good, I would not trust it. I,
Okay.
I, I know that's not what you want to hear, but
Yeah.
but it's the reality is when it seems too good, it probably is. So I will go back after this and I will double check for duplicates and I will find my smoke widget and I'll run it in that and we'll see. But that's the kind of scrutiny where you always have to do that. And always be aware, like for instance, notice, see the two here? That meant I duplicated it. Therefore,
Okay.
I didn't remember that I still had that checked. You just have to be very vigilant. Any other questions about class imbalance? All right, let's move on to unsupervised learning. And I will say, as an aside, this week out of Australia, they announced an AI program that'll do unsupervised learning and is probably more accurate and hopefully more user friendly. Because let me just digress a bit about the background, and it's in the chapters I told you all about, is that unsupervised learning has a real role in medicine. It was used early on for genomic data where you had a SNP, which is like a genetic anomaly or abnormality, and they wanted to see what it correlated with or what did it go with. What phenotypical characteristics does this genotypic abnormality fit with? Uh, and so that's where unsupervised learning came in handy, is you combined all this information And then it would say, well, this group goes with this group. Another example in the book came from an article from the COVID era where they looked at unsupervised learning from a bunch of ICU data. There was no target per se, it was just ICU data. And so when they use clustering, which is a major way to do unsupervised learning, they had 4 clusters. No surprise. The 4 clusters went something like this. Cluster number 1, they sailed through the ICU and got out, quickly. Number 2, they were there, 3 or 4 days. Number 4, they were in there for a week. Or 3, they were in a week. Number 5, they died. So that it was pretty logical clusters. And again, so if, for instance, you have public health data, uh, and you have no target, there is no goal other than you want to see if you have interesting clusters. That's how it can be used. And I'm going to show you in a second how I used it for Florida sort of public health data, if you will. So it's good when you're trying to look for clusters or groups. Now let's start with the breast cancer Wisconsin group, which is a classification group. It came from the data sets, by the way. It consists of a bunch of cellular characteristics of malignancy versus non-malignancy. So if you look here under type is malignant or not malignant, you see it's not class imbalance, although it's almost 2 to 1. But so benign and malignant is the outcome. So, but nonetheless, I use this for k-means. Select columns was to get rid of the type. I don't need the target, okay? And so k-means, let me try to explain how this works. You have to guess what the ideal k is, which is the number of groups, okay? You start with a couple, but you can use the silhouette score that's automatic in orange. The higher, the better. But notice these scores are pretty close, and you may have to decide whether really 2 or 3 groups is the best. There are several ways to do that, but let's just say we're going to use 2, and let's look further. So when you look at a data table, notice that now you've got a new variable, and notice it gives you the silhouette score on each one of these, but it's a new column of cluster. And it goes down what the other variables are. So again, in this data set, it looks like mitoses. So no, surprise here that those with more mitoses were malignant cells, as just an example. But so the question would be, let's look a little bit further at distributions. Now you're looking at cluster 1 and cluster 2, the frequency. Does that look familiar? It looks like it's identifying benign and malignant. And that's probably what it's doing, I might add. Scatter plot. Well, let me, before I do that, so there's a second, so you've got one tool here to help you. The silhouette score helps you decide 2 versus 3. Often they're not that close, by the way. These are pretty darn close. But the silhouette score gives you a little bit of information. Let me try to increase this in size. That's pretty good. I like that. What you might say, what's this blue tail? Those are ones that are a little bit outside the cluster. They semi-belong. They're not wrong. They're just not as clean. So the cluster is not as pure. Does that make sense? It's just not quite as good. But I like 2. But again, you could do, let's do 3. What the heck? But what you what you want to see, this is what I don't like. So you've got a cluster that's pretty tiny. I'm going to stick with 2 clusters. So we got 2 clusters. Scatter plot, again, you can do a bunch of different things here. We need to go back and change it to 2. Okay. So visually you can see this, but you can do a variety of things, play around with it, and just look at different parameters, like where's mitoses here? So I see more mitoses. Uh, anyway, this gives you a way of visualizing these clusters, if you will, you know, mixing and matching those. And I think that's enough said about it. So this, again, what this I think did is even though we removed the target, it identified the fact that there are two groups in here, benign and malignant. Does that make sense? But that also tells you, let's say you have a data set, it might identify a data set and you turn around and go, wow, it seemed to identify X. I'm going to create a classification model of that X and try to see what predicts X. So again, I think that the groups that it selected were simply benign and malignant. But you know, you might have a data set where that target has not been identified. All right, let's look at another thing that you can do that's kind of cool. We've not talked about paint data. What's fun about that, first of all, you got an X and a Y axis. You can go in and see C1, C2, C3. You can create as many data points as you want. So I created 3 clusters for demonstration purposes, right? Under k-means, let's see what the cluster. It says 3 clusters, and I think we know there's 3 clusters, so it's right. So let's look at the silhouette plot. 1, 2, 3 looks pretty good, other than that little tail. I like 3 clusters. And scatter plot, you can see 3 here using clusters. So again, all that did was show you that it's pretty good in determining the number of them. But remember this, if you ever want to try to create your own little model of data points on X and Y, paint data is kind of a cool tool. All right, so let's look at a couple of other things. I have a data set that came from a study in Virginia where they went into some rural counties and they looked at only African American adults. They looked at sort of risk factors for heart disease and diabetes and just had a bunch of data with no target, nothing. And so, again, it's kind of unsupervised, pretty messy data, I might add. So that's why I made sure I imputed the missing data. And let's see, what did I do under select column? Oh, I got rid of some stuff that didn't amount to anything. That's why there's select columns. K-means not very high silhouette scores. The highest one was 2. And then the silhouette score plot, see how clean, pretty good. But again, obviously cluster 2 has some borderline identifications, so to speak. Some cousins, but not direct relationships, if you will. All right, let's try it a different way, my preferred way. Same select, these are reversed, but it doesn't make any difference. We're doing the same thing. We're getting rid of stuff that we're not want to measure. We're going ahead with the pre-process. And now we're doing distances. We're going to do distances which, and confused matter, look at all the different ways you can measure distance. I'm going to use Euclidean only and columns only, but let me show why this is interesting. Now, when you look at it, and unfortunately, this gives you more options. I'm selecting Ward. You could go with average, for instance. And so there are several different here, weighted. I don't think it changed much, but the point is, yeah, you'd have to play with that. But so here, it's saying I've found some groups in C3. Well, actually, C2 is interesting. I'm not buying that. I have to go back. Why is there one group of immediate frame, only medium frames? Unless it's a large group, that may be what it is. But in any case, in this group, actually, I'm not positive whether gender female belongs in the C2 or C3. But HDL and frame small seems to be a cluster. Let's look at, we could try cosine. Let me just try another option and just see if it changes. Yeah, it did change. So again, here we go with trying different things. Let's look at Word again. I'm going to go with the weighted average, that it's simply saying that it believes there's two groups. And again, it's a little hard without exploring this to know what it's finding. It seems to be finding a male group and a female group, and it looks like it's saying that the males likely have more blood pressure issues and whatnot. But let me, it's just the nice thing about hierarchical clustering when you select column is it actually shows you what it's looking at in each cluster. Whereas k-means clustering doesn't tell you what's in the cluster. So let's use a better example. I'm not sure that's a particularly good example. Are you all aware that every state pretty much participates with something called health ranking, county health ranking? This is self-reported, but it's kind of interesting information. So when you go into the state of Florida, which is where I live, 67 counties, it does this very interesting, and it's all numerical data. And I should have mentioned, when you do clustering, the data has to be number one, numeric. Orange will convert it to numerical for you. It also has to be scaled. In other words, you can't have something that's 100,000 and the next variable's 10. So it normalizes or standardizes it. So that's all done for you. But if you look at these variables, and there's 41 of them, notice they're very interesting. There's some of the what I would consider very important public health parameters. Income, free lunch. They're things that you would worry about if you're worried about poverty in counties or poverty in your state, violent crime, you know, teenage pregnancy, on and on and on. Okay, so this one I decided we'd do both and take a look. So let's look at distances, columns, hierarchical. I think this is a better one, by the way, because if you look at these clusters, basically you have healthy people doing well, and down here you have people struggling. So is that earth-shaking? No. But it basically, that's what it did, is it clumped these risk factors into healthy and these risk factors into unhealthy. And unfortunately, unhealthy outweigh the healthy. All right, so let's look at k-means clustering. Actually, now I'm confused. Where is the silhouette? score. Huh. I'm not quite sure why the silhouette score disappeared. Here's the silhouette plot. Let's look at that. So here again, two groups, not perfect because you see this tail here, but again, there was a silhouette score and it was 2. Uh, and the distributions, you can look at different things here. So this allows you to look at, the distribution of the different categories. Here's a box plot, which is helpful because you could look by. So now here's another way to look by cluster because that's what you really want to know. All right, let's look at C1 versus C2. We can pick most anything you want to, physically unhealthy days. So they're greater in C1 than C2. Let's look at mentally unhealthy. That's not statistically significant. Smokers, a little bit higher in C1 than C2. How about obese? And again, self-reported, so I don't know quite to make of it, but look like more obese patients in C1. Physically inactive, more in C1 than C2. Birth rate, higher in C1, a lot higher. Wow, almost double. So my point is, you might have been able to figure this out on your own. And Philip just logged on, so I want to show him, I want to go back over this. Every state publishes, to my knowledge, publishes some self-reported quality of life parameters for their citizens. You just go to county health ranking, pick your state, and hopefully it's self-explanatory. So when you look at this, there's 41 features that are self-reported and 67 because there's only 67 counties in Florida. But they're important from the standpoint of public health, really important. So the whole goal here was, are there any clusters? And the answer was both k-means clustering and hierarchical clustering says, yeah, you have two clusters. And so one of the points here I want to make also is notice that you also can save this if you wanted to. Here's C1 and C2, and you could even use that as a variable itself. And you can do that by just saving data. So the reason for putting the data table in there is you could show which one, this one is C2 with a silhouette score. Remember, the higher it is, the more likely it belongs to C2. It just sort of tells you what these clusters are about. But again, the box plot, I think, is very meaningful here, where you can start looking at these clusters and saying, all right, here's the primary care physician. Wow, that's greater than 2 to 1. So C2 is able to see doctors more than C1. Does that make sense? So you would do the same. I mean, this is happens to be county health data, but it could be anything. ICU data, could be admissions, could be anything where you don't yet have a target. You're just exploring it. And so this is an example I give you where we use both hierarchical clustering and k-means. And they probably don't always agree. You could do both, I might add. So this is the whole idea is to try to find groups that you don't know about, that you haven't seen before. Any questions about this? I know this is a little bit short and it's a little bit complex. And yes, there's some art to this. It's not all science. And yes, you can ask programs, AI, to do this. Please create or please look for the ideal number of clusters using k-means clustering and select the highest silhouette score. There's also called the elbow tool. Tell them to use both and see what it finds. So you can use AI to do this, but this gives you what's nice about this is you see exactly what you find and you can go further. And AI, it does it, but you don't know exactly what it did. That's the problem. But this gives you a way of taking raw data and trying to see if you have clusters. And as I mentioned, you could create this. For instance, we were fairly sure that we have two clusters. You could create a classification scheme to try to, and let's say, I've forgotten, I think C1 is the unhealthy one, I believe, but you could create a classification model to predict C1, right? So if C1 is what's interesting to you, you could then have that as a column, and then you could create the model and predict C1. It's probably going to show you the same stuff you already know, but you could do that and see how good the model is. So I've not done it, but I could do it. It would be easy. Does that make sense?
So in Dr. Hoyt, if that is the case, are we going to have like a testing data separately or like use the same data set? If we are
Uh,
like,
no, you would say this, but actually, now that you mention it, let's, for the heck of it, let's see what happens. I'm assuming you'd use the saved data, but there's so many widgets. Let's just see what happens here. Well, the problem is you'd have to select the target, so this would not work. So let's get rid of that. So let's save the data. If, we got time, I guess. Yeah. Let's go ahead and do that. Save it to the download as, okay, so it should be saved in my download file. So let's, remember we have to set the target. Let's set that as the target because it's C1 and C2, right?
Mhm.
Oh, wait a minute. The reason remember again, we had this set on test, right? Needs to be set on train. So, and I think we said we wanted to predict C1, right?
Yeah.
Strong model, huh? Very strong model. But I'm hoping that'll help you all see the relationship between finding clusters and classification. It's possible that you start with unsupervised learning and move to supervise. And so you could put in here, let's put in here rank. You could do feature importance. Let's see what overall it thinks is the most important in terms of information gain. And let me blow that up. So it's actually saying percent physically inactive. So again, if you work for the county or the VA, whoever, you might say, wow, it looks like physically inactivity was the most important factor related to that cluster. And again, that cluster, low income, rural. Now, Asian, I'd have to look at that. But anyway, I'm just showing you that's one way to do it. And then obviously, while we're at it, look at cluster 2. Nah, that doesn't make sense. It should not be the same for cluster 1 and cluster 2. Yeah, I would have to, anyway, I'd have to work through that to figure out why it's given the same results. Something, it may be the way it was copied to save data is not correct. It may be that I should have saved data from some other, maybe straight from k-means. But the point is, you do have the ability to save the clusters and analyze those further. So that gives you one more variable, if you will. Any questions on that? All right, any other, I asked this before everybody had logged on. Any other thoughts about future sessions? Because I don't have any plan, but I would consider them if it was simply, a session perhaps to talk more on update on data science and AI or something of that nature. But you can feel free to email me if you have further thoughts about it. Any comment or discussion about that?
Hey, sir, I'll probably send you an email later, just on some questions I had.
Okay, fair enough. But if you have other ideas down the road, let me know, because again, I've got a website and other ways that I can post information and education and whatnot. So otherwise, I appreciate your participation, and it's been fun for me, and it always gives me a chance to exercise Orange a bit and look at new data sets and whatnot. So stay in touch. Thanks for, again, tuning in, and hopefully maybe we'll meet down the road virtually or otherwise.
Sir, I have a question.
Sure.
Are you going to be doing the next session for AI with Dr. Chang? Are you going to be doing any lectures
In fact, that was today. That was one of the reasons I didn't do today.
for the advanced course?
Yes, I will be there for the advanced course.
Okay, fantastic.
So, yeah. So we hope everybody takes one of those courses. It's worth doing. We hope you consider the Medical Intelligence Society, and we hope you know about office hours every Wednesday. They're all worthwhile endeavors. Does everybody know about office hours?
Yes.
Okay.
Yeah. Mhm.
All right. Well, feel free to email me or text me or whatever, and happy to stay in touch and answer any questions you have. But enjoyed it. You all take care. Keep learning.
Thank you.
Thank you.
Thank you so
See
much,
you
Dr.
later.
Hoyt.
Okay. My pleasure.
Thank you, sir. Appreciate it.
Okay. Bye-bye.
Thank you. Bye-bye.